here what a cluster analysis is and how to do it. So cluster analysis is basically a way of classifying data into similar groups, and it requires methods for measuring distances like dissimilarity measures. So yeah, it's basically the basics of what a cluster analysis does. So I'm going to go over the data. First, we're going to pull it up. Here's a library, read Excel, telling me we want to read an Excel file because that's the type my data is. We're going to name that data file cluster data. That's where it's located. I'm going to run that. So yeah, this is where the data was located. This is the column types. They're all numeric. So we're saying combine all these numeric things and then view that. And it'll bring us here. So CWBs are basically count of work behaviors. OCBs are organizational citizenship behaviors. Missed days are the amount of days they've not been there. So also like absenteeism. Age is how old they are, and years is the amount of years they've been at the company. So this is a count of all the CWBs they've done since they've been in the company, OCBs since they've been in the company, the absenteeism, their age, and their years. So that's how we view all that. And then these are the packages that we'll need to install. I have a hashtag there just so that I don't run it on accident, but if you took it away, you see that you'd put instill.packages and you'd put the open parentheses and then with quotation marks, the name of the package, which is tidyverse. Oops, didn't do that. And the ones we'll need here are tidyverse, cluster, facto, extra, vegan, FPC, and nbclust. I'm gonna load these all up. This one specifically, tidyverse, is with data manipulation, clusters with clustering algorithms, and facto extras clustering algorithms, visualizations. These are used later on. Some are in the validation aspect, but load them all ahead of time, but typically the easiest. So we're gonna go to data cleaning time. Now this part's important. You wanna put the name of where you're gonna load all of the cleaning you're doing, and you're gonna wanna refer to that data set throughout. So I called it cluster data, the same as the original data frame we had, just to make it a little easier on myself so I didn't get too in the weeds with so many different names of different data frames up there. So we're going to do that. So cluster data is where we're loading all this in na.omit cluster data that removes missing data points. And then cluster data scale, open parentheses, that standardizes the data. So I'm going to go ahead and run those. Now, if you want to see exactly what they're doing, because down here we can just highlight over this part, not the name itself, and run that, and we can see all the standardized numbers right here. And similarly, we can go right here and see them scaled. Perfect. Are these standard, Oh, sorry. This would show the missing data points, and this would show that it's scaled. And then right here, head, you can check there that it all happened. And yeah, no missing data points. It's all been standardized. You can see that there. Perfect. Now we're going to go and make a correlation-based distance method. So we're going to decide how to cluster the data this way. We're going to call this one CoreDist, just to give me a simplicity of like this data frame we're going to refer to as the correlation distance method. So we're calling this one CoreDist. We're loading all this into that. That's what this means right here. Get_dist is basically saying I want the distance kitten. Cluster data, that's the data set here we're referring to make this one. Comma is separating it. Method equals Pearson's. We're going to separate these into clusters by the Pearson's methodology of splitting it up. It's a stat you can run. All right, so I'm going to run that. And then similarly, we are rounding them up, see, as the matrix goes for this to the second numerical variable, and we're looking at 1 through 6. Cool. So now we're visualizing the dissimilarity matrix. Gonna run that. So we can kind of see what we just created here. So we basically created this dissimilarity matrix. Kind of chaotic, but we can see that as we go higher up, they have more of a they're not as similar up here, more similar down here. That's where the value is. But let's see more about this and validate it along the way. So we're going to get into that. First, we're going to relative cluster validation. So this determines the optimal number of clusters you can have. Enhanced k-means clustering using k-means is typically the best way to go about this. And the recommended amount for this number to start at is 25, so we're going to go with that. Algorithm to find the groups, basically. So what is k-means enhanced clustering? It's an algorithm to find the groups from an unidentified amount. So I'm going to go into that. Oh, see, can't forget to get everything there. It's going to bootstrap all of that too with it. So we're calling this one K-clust. We're loading all that into K-clust. E-clust, that's the type of methodology we're wanting to put in. Open parentheses cluster data, that's the data frame we're referring to that we made up there. K-means n equals start 25. So we can see here the K-means clustering, the different groups that have evolved. We've got 6 groups, which I think is pretty cool, 6 clusters that we've created here. So yeah, we can see where they fall in each dimension and all that. It's very interesting stuff. All right, so now we're going to do a gap statistic plot. This basically shows the optimum amount of clusters. So we've just clustered it. Is this the correct amount of clusters we should be doing? Is this the most? We'll see. We're going to run this and find out. So fviz underscore gap underscore stat is what helps us see this. We would put k-clust because that's the variable we just created here. And gap start. So that's just basically the $ gap start is the part of that we want to. We want to look at the gap start created for k in this k-cluster right here that we've created. So yeah, this whole thing was basically creating this k-cluster. All right. So we can see right here the number of k-clusters 6. So it's saying the optimum amount of clusters is 6. We can see here on the gap statistics, we're kind of seeing, what you can tell by the way this goes up, right? Okay, much better gap statistic, much better. Okay, and then we're kind of leveling off. So the most benefits here coming from that 6. All right, now we're going to go at the optimum number of clusters using the gap statistics. It'll tell us right here, 6. So it's another way of just getting that same information, but without the graph. I like the graph though. And then printing the results. So we can kind of see right here all the information about how it got there, the clustering vectors, the k-means, all that stuff. So now we're going to do some, all of this right here was kind of relative cluster validation, helping determine the optimum amount of clusters and making sure that we picked a correct amount when we first ran it here. So now we're going to look at internal cluster validation, which is basically the goodness of a clustering structure, how appropriate the model is based on the data we have, and how does the model work with that data that we have. Are we creating the best model for the data we have, basically? So we're going to do a silhouette plot for that. What is a silhouette plot? It's the average distance between clusters. And so fviz underscore silhouette is the code, the code to do that. Open parentheses k-clust, because that's the data we are referring to that we created up here. So we can see here that the average silhouette width is 0.38, so it's a pretty decent silhouette width. And then here are the clusters and each color coded. We can see down here the width for each cluster, the size of each cluster, and the name of it. So each cluster has a decent amount of people in each cluster. So we've got some good support here. So let's look at the external cluster validation. So we're comparing the cluster analysis results to a known result here. Other ways of doing this are a RAND index or a MELAS VI, but this is basically just making sure that this cluster analysis kind of correlates well with something else that we know. And we're going to compare it here to the data for the age against the k-cluster in a table. And there was an error. Oh, I think I know what it was. Problem here is the cluster data we created up here, we standardize all of it, and now it can't work because it's an atomic vector, a standardized vector. So let me just erase the global environment up here. And not run that stuff. So what I'm doing here is you could have named it something different so this didn't happen. So how to avoid this error would have been like, see how we're all loading this in the cluster data, calling it something different instead of cluster data and referring to, every time we're referring to cluster data here, calling it something else. So calling it, I don't know, except for down here at the bottom. That way we don't have all the standardization into it. But I did not realize I did that until just now making this video. So we are going to run the library and all this beginning stuff like we did. And then we're going to skip that part. But run all this so that we can make the K-class thing. Boom. Okay, we're good. And then I'm gonna run this. And we should be a boy now. All right, here we go. So down here, we can see when we compare the cluster data, so the non-standardized cluster data that we had at the very beginning, against the K clusters we created, we can see that it kind of all comes out where it correlates each age, kind of relates with one of these clusters in a way that makes sense where each age is counted for. So if you had more like discrete categories, you'd be able to see here each of those. But yeah, that's how you go about clustering in R.